Hello students, today I will be discussed about aliphatic nucleophilic substitution reaction. So this is in your mechanism part, organic chemistry mechanism of reaction. So first of all we have to realize the term including here. Okay. So this one is aliphatic. We know that Newton is aliphatic, aromatic or other. So this part we all know it. Nucleophilic. That means some nucleophile will be involved in these reactions, and this is substitution. Substitution means one part of a molecule will be replaced by the nucleophile. Okay, replaced by the nucleophile or substituted by the nucleophile. That's why this one is called substitution, and we know the reaction. Here always the substitution occurs at sp3 center. Okay. Always it will occur in sp3 center. Now this carbon here sp3 now one of the nucleophile which come and react to give the corresponding RNU plus X. So look at this way. So this is a general reaction. So in these cases this will act as the nucleophile. Clearly this one will be the nucleophile. This one is the substrate, that is aliphatic substrate, which one is sp3 based carbon is present there. And of course this one will be the product here, and if we look here, that is this part. Okay, this part is replaced by this part or substituted by this part, and this one is called the leaving group. Okay, this one is called its leaving group. It eliminates with its electron. Okay, here the lone pair, here the one electron pair goes to here, so it will eliminate with its bonding electron pair. So this is actually the general reaction of a substitution. Which one is called the substitution reaction? It can be categorized by this way. First one is SN1 reaction. Okay. Second one is the SN2. Third one is SNI, and these are the less important. Fourth and fifth is SN1 prime and SN2 prime. Actually these are nothing but the allylic arrangement, will be discussed in later. Okay, so first I have discussed about details on SN1 reaction. Okay, so I will go first the SN1 reaction. This one reaction mechanism, how this one occurs and what is its characteristics or others. Okay, so I have to know that the SN1 reaction is a two-step process. Okay, so it's a two-step process. Two-step process. You can consult any standard textbook or books on reaction mechanism. You will go and got this. So it's two-step process means must involve an intermediate. Okay, must involve the intermediate. Here this intermediate is the carbocation intermediate. All of you know which one is called the carbocation intermediate, must involve on the carbocation intermediate. And what is this term? This is substitution, this is nucleophilic, and one it stands for unimolecular. Okay, why it is unimolecular I will come later after this. The full name of this one: substitution, nucleophilic and unimolecular. So this is a two-step process. So now if I want to draw the general mechanism of the SN1 reaction, I want to draw the general mechanism of the SN2 reaction, then it looks like this. So this will be the mechanism of SN1 reaction. This is general mechanism based. So as it is two steps, so the first step, that means step 1. Step 1 will be involved just like this, that is the Rx, and it can decompose in presence of solvent. That is very important here. What is the role of solvent I will discuss later. So in presence of solvent, this will decompose just like this, R plus X minus, and this step is the slow step of this reaction, and consequently this will be the rate determining step, or simply called the RDS. So this is the living group here. Clearly this one is the living group and this one intermediate carbocation is formed. What should be happening in the step 2? So in the step 2, that R plus now react with the nucleophile present in the system. Okay, present in the system, it's maybe solvent. When nucleophile but solvent act is the nucleophile, that reaction is called the solvolysis reaction. So now this one is the first step reaction, and we got the actual product, that is R. So this will be the product for this one. So here this is an intermediate, yes or no? This is called the intermediate. This is not the product and not the substrate, it will be formed in the intermediate step of the reaction, that's why this is called the intermediate. Clearly this one is what? This one is carbocation. Okay, this one is called the carbocation. The reaction is also known as what? First elimination and then addition. So this reaction is called also the elimination followed by addition. Yes or no? This nucleophile added to this, and this one first living group is first eliminated from the substrate, and that's why this one is called the and this step must be always, first step must always be solvent. If solvent is not present, then the energy required for this reaction is very much. Now if we take an example, what is the role of the solvent here? So what is the role of solvent here? I can take an example of substrate is tertiary butyl chloride. Okay, if your substrate is tertiary butyl chloride, if your reactant is this one, R is equals to tertiary butyl group and X equals to chlorine. And in gas phase reaction, if you carried out this reaction in gas phase, then the energy required to break this bond in this case will be 630 kilojoule per mole. Okay, so that huge amount of energy is necessary to break this bond or carry out this reaction. But in presence of solvent, in solution, that's why this will be in solution, some solvent, a suitable solvent should be present there. What kind of solvent is necessary will be discussed in separate part. The energy required is only 84 kilojoule per mole. So look at the difference. So why such amount of energy difference is there? So gas phase reaction is only occurs at high temperature. It may not be possible to reach in our laboratory easily. That's why we always accomplish the reaction accompanied by a solvent, suitable solvent. So we discuss later with polar protic solvents will favor this reaction. So what is the role of here? Now in these cases, the intermediate, that is carbocation and the living group, both are stabilized by the solvation in presence of solvent. That's why the energy is compensated. There is a solvation energy will be come from there, which will compensate the required amount of energy to break this bond. Okay, we will be discussing later what kind of solvation is occurs there. So now come to the characteristics of SN1 reaction. So these are very important part of this reaction. So up to this we will discuss about the general features, the general mechanism of the SN1 reaction. Now I discuss what the characteristics of the SN1 reaction. First, that is the energy profile. There is an energy profile diagram of this one. I may call this as a potential energy diagram, or you may call this as the energy profile of this reaction. Okay, energy profile of this reaction. So now if we take this potential energy, and all of you know to here the reaction coordinates equals to here. Then if this one is substrate, okay, this one is substrate and here Rx. Okay, this one will act as the substrate here, and the energy required to this goes to here, and this goes to here, and this goes to this. Okay, this will be RMU. Product will be there, and this is the intermediate R plus, and this is transition state 1, and this is transition state 2. So look at this, the energy required, activation energy required for this first step is higher than the second step. This one is the second step, the required amount of energy in this case is second step. So by this way we can explain why the first step, that is formation, if you can consider it is a two reaction, that is the first step reaction will be this one. Okay, so in these cases this one is endothermic reaction, so we must supply some energy through solvation or other. So it required higher activation energy to reach this transition state and collapse to the Rx plus X minus. So that is not the actually intermediate, this one actually intermediate. So look at this, if R is more stable, then this energy will be lower, that means this deep will be more deeper. If R is more stable, then this deep will be more deeper, because we know that higher energy means lower stability, and lower energy means higher stability. So if the R plus is higher, then its energy will be lower. So, and the second step, look at the second step, if you consider this one is, now this one is starting with 12, and Nu minus is present here, and it will react with this and gives the corresponding product. Its required activation energy is lower. So this step is faster and this step is slower. So by this way you can explain why the first step is the RDS. Okay, so clearly this step is RDS. That is the first step is RDS. So this one is the number 1. Then we come to the number 2 is kinetics of this reaction. Okay, so now kinetics. What is the kinetics of this reaction? Clearly, only one substrate. Look at this. Only substrate is involved in the RDS. Yes or no? Of course, only one species is involved in the RDS. So rate of this reaction will be equals to what? Now concentration of rate of this reaction will depends on this. So rate of this reaction will be equals to K1, that means only one, that's why 1 you may write is K, or you may give the K1, it's not matter. So X to the power 1 here should not be written 1, as only one molecule is involved here, that's why this reaction is how many order, as 1 is present here, so this is first, this one is first order kinetics or reaction. Okay, first order kinetics. It follows the first order kinetics also. As only one molecule is involved in this reaction, that's why this one is unimolecular. Understand? Unimolecular. So why this reaction is called unimolecular? We cannot explain this one. How many molecules involved in the RDS? When we studied SN2, this reaction will be bimolecular. 2 stands for bimolecular. 2 species will be involved in the RDS. That's why that will be bimolecular. Now come to the unimolecular, so SN1 reaction. So that one is due to this one. It's called the unimolecular of this reaction. Now, number 3, if it comes to characteristics, now come to characteristics in the number 3, that is the dependence of rate of the reaction. How the rate of reaction will be. It is obvious that all the reaction may not proceed in same speed. All the SN1 reaction may not proceed in the same speed. Now, which reactions? Some reaction give faster rate reaction, which is very much slower, or other. So, what depends? Rate of reaction. That means SN1 reaction. Of course, the rate of SN1 reaction depends on. Okay, depends on. Started with the substrate. Yes or no? Substrate. So if we consider the substrate dependence, that is only nature of substrate. Okay, nature of substrate. So now we will discuss which substrate gives the faster SN1 reaction. That is the So it's very simple. You have to be forward for the first step reaction. The reaction which will give the first step very quickly or faster rate, that will be the faster reaction will be given by that substrate. So now that is the Rx to R plus X minus. So this one goes to here. So if this one is more stable, okay, more stable, that means what? Of course, rate will be faster. So we know all about this, that is the stability of the carbocation. What? 3 degree is more stable, then 2 degree, then 1 degree, and then the methyl cation. Yes or no? So how this rate of reaction is different? So if we consider this, that is CH3 whole 3, and this, now take this one is fluorine, okay. So clearly this one is 3 degree alkyl halide, so it will gives the 3 degree carbocation. And now if we consider CH3 whole 2 CHCl, and this one is considered CH3 CH2Cl, and last one is CH3Cl. Clearly, so in this case is methyl cation, this is 1 degree, and this one is 2 degree cation. 2 degree substrate or gives the corresponding 2 degree cation. So clearly this will gives the faster rate reaction or not. So by this way, substrate which can gives the stable carbocation give the faster rate reaction. So we may take other examples so that other factors may consider and we give this. Why this one is more stable? That is plus I effect and hyperconjugation. We know all about this. Now the second example of the substrate dependence is this one. So look at this substrate, that is CH3O CH2Cl, because the lone pair is present here. This is the heteroatom present in the alpha position, and this is the reactive carbon. Here the reactive center is this one. Of course, the reactive center is this one, and all are sp3 hybridized. So now, if this one is carried out this reaction, so what will be happening here? Now first this Cl minus will be eliminated, and CH3O CH2 plus. Look at this. This one is 1 degree carbocation, but this lone pair can stabilizes this with through resonance. So we got the another, that is CH3O double bond CH2 and plus charge will be present. Yes or no? That's why such kind of species are also favorable for SN1 reaction. Now we may carry out this reaction into water is present there, then we will give the corresponding products. Yes? So this one is corresponding products. Goes to here. Now second one is the nature of living group. So now first one is A, and now B is the nature of, okay, so nature of will be here, that is the living group. Look at this, nature of living group. The second part of this, how the reaction is different. You have to collect the more examples from your book so that the substrate dependence can be very much clear. Now the living group. So now if we look at this reaction, that is Rx, then R plus plus X minus. Okay. So when all the R are same, now X is different. X is different. So when this reaction will be faster, that means after leaving, it will be more stable. Yes or no? If it will be more stable, then it can be leaves easily. More stable, that means lesser energy. Lesser energy. The species after leave from the substrate, if this species is more stable, then it will be a very good living. Okay. So what is the dependency of this? Now, if the living group is very good, rate of SN1 reaction is increases. If the living group is very good, then rate of what? Rate of SN1 reaction will be increases. Yes or no? Rate of SN1 reaction will be increases. So it's X, how X will be doing? Now in solution, take an example of this one. If X equals to I minus, after elimination X I minus, then it will be Br minus, then it will be Cr minus, then it will be F minus in solution. So down the group, okay, down the group F, Cl, Br, I. Down the group, the nucleophilicity is increased. This is one of the cause. Other causes are there, just like this, that is Rs, and it's the nucleophile. So now if we take in this OTS minus, yes or no? TS minus, that is OTS tosylate is much more stable. How this one is stable? I will give an example of this one, that is how this living group is very much stable. Okay, how this living group is very much stable. So that means take this one, that is tosylate. What is the structure of this one? That is this one is called tosylate. S double bond O and O minus. This one is this, and the paratoluene group is called paratoluene sulfate. If you look this cases, this will be resonance stabilized, and then this will come to here and here, etc. So you can write down the order of the stability of this one, that is CH3 double bond O and double bond O, etc. will be there. So clearly the tosylate is highly conjugated. That means it can be resonance stabilized, so its energy will be lower and more stable. Yes or no? So this one will be more stable. As this one will be more stable, so it will act as the good living group. So now, if this one is NO2, then this will call nosylate. If this one is called bromine, this one will be brosylate. By this way, we can change this one. Now another is this, that is S double bond O and O minus. If this one is CF3, this one is called triflate. Okay, triflate is known as the super living group. Okay, so by this way, so when such kind of living group, that is the good living group, attached to the substrate, the rate of reaction will be much faster. Now that is the number C, that is nature of course now this will be nucleophile, that is Nu minus. Okay, nucleophile, that is the Nu minus. So how the Nu minus? So look at this. This one is the RDS, this one was the RDS. No nucleophile is involved in these cases. Yes or no? No nucleophile is involved in these cases. That's why the rate of SN1 reaction does not depends on the nature of nucleophile. Okay, so nature of nucleophile does not depends or changes the rate of a SN1 reaction, as this one is not involved in the RTS. So this one is number 3. Then number 4 one is the stereochemistry. Okay? So what is the stereochemistry of this SN1 reaction? Look at this, the SN1 reaction, if this R is chiral, if this one is chiral carbon, okay, so this one is chiral, then after this it will give this one, that is R plus and plus X minus. So when the nucleophile may come from this side or nucleophile may come from this side, yes or no, nucleophile may come from this side. As the carbocation is a planar species, so if this one is the structure of carbocation, as this one is planar, so nucleophile may come to here or nucleophile may come to attack from here. So we may write this one is there, that is the one species, this is another, and this one is this, another, and this one is plus. So look at this. So this group are this one is in plane, another is above the plane, another is below the plane. So this is this side and it may come from this side. So theoretically the 50% attack from this one is different R1, R2 and R3, as this one is chiral. So this 3 should be different. These 3 should be different, R1, R2 and so what will be the product? Now if attack from this side, if this give positive or capital R, now if this is attack from this side, of course this will be negative, that is laboratory or S. So always we get the plus minus, that means called the racemic mixture. So this is the theoretically we got this one, that is the racemic mixture is the product expected in the S1 reaction. Why we call the expected? So I think you have to clear why this one is racemic mixture is given. So now come to here, why this one is expected. Slightly we may call, as this one is from this side, so this is actually called the retention of product and this is the inversion of product. Slightly inversion is higher because such kind of tight ion pair may form there. Okay, ion pair may forms there. Look at this. When X want to leave this one, but X is R has different charge, so it can held it strongly. So this side is now blocked for few moment. This side is blocked by the X minus, but this side is totally free here. That's why the inversion product will be slightly higher. That's 5248 or 5347. This is the reversion of it. So this is the theory why the product is not 100% racemic but slightly inversion. But you have to be asked the question, then you will go to this racemic in nature. This one is the racemic in nature. So this one is the number 4. Then we come number 5, that is characteristics of the SN1 reaction. Number 5, dependence of the solvent in this reaction. That is another very important part of the SN1 reaction. What kind of solvents favors the, so now the nature of solvents. Okay. Nature of solvents. Simply you can told this that polar protic, okay, polar protic solvent favors the SN1 reaction. Okay, polar protic solvent favors the SN1 reaction. Okay, polar protic solvent favors the SN1 reaction. Why? So that is the question. So again goes to the first step of this reaction. It may occur by this, that is this minus X, delta minus and delta plus. So this is the transition state 1. Yes, of this transition state 1. Then this will collapse to the corresponding R plus X minus. Yes, of this will be collapse. The electronegativity difference is there. That's why just kind of. So if the solvent is polar protic in nature, then its negative side attack this solvent, this one, okay, positive side will be of the solvent. These are actually the solvent. These are the solvent molecules, and in this cases positive charge will come and stabilizes this part also. Okay, positive charge. So what should happen there? This transition state is now more stable in presence of the polar protic solvent. It should be plus, it should be minus. Okay. So polar protic solvent, 2 parts will be there. Look at, take an example of water. So this will be delta plus and delta minus. So this one will be the minus. So delta minus, that's when now oxygen will comes to here and the hydrogen will goes to here. So this is an example of polar protic solvent. Its dielectric constant is also very much higher, highest dielectric constant. So the energy required, that is the substrate, and this one is transition state 1, and in this case is the transition state 1. So this one is in presence of non-polar solvent. Okay, non-polar solvent. So in presence of the non-polar solvent, the required amount of energy will be higher, but in this case this will be polar protic solvent. So as this one is stabilized by the solvation, so its energy will be lower than this, and it needed lesser amount of energy, or activation energy will be lower in presence of this solvent. That's why we told that polar protic solvent favors the SN1 reaction. So we can take an example that polar protic solvent, if the dielectric constant of the solvent is increases, then how the rate of reaction increases. This was the theory why polar protic solvent favors this one. And another, that is in gas phase. In gas phase we need very much amount of energy, but in these cases when such kind of solvation occurs there, then its energy will be compensated. Required amount for dissociation of the bond is compensated by this. So now come to the example of an this one. So reaction of, used to black ink, that is reaction of tertiary nucleophile. Reaction solvolysis, okay, solvolysis, and then reaction is not required. Solvolysis of tertiary butyl. I have already told what is the definition of solvolysis. Solvolysis means solvent act as the nucleophile. So no added nucleophile is necessary here. So now if the solvent is this one, the dielectric constant. So this means the dielectric constant of that solvent, and this one is called the relative rate. Okay, relative rate of this reaction. How the relative rate is depends here. So if I take the acetic acid, clearly this one is polar protic solvent, and its dielectric constant is only 6. Let this one is 1. That is the relative rate, not the exact rate. Second one is methanol. Its dielectric constant is 53, and its rate is slightly increases. Now if this one is formic acid, okay, this one is formic acid, then its dielectric constant is 58. Now the rate is increases, relative rate is increases up to 5000. And if this one is water, okay, its dielectric constant is 78, and the reaction relative rate of this reaction. So as the dielectric constant increases, the relative rate of the reaction increases. All of these are polar protic solvent, yes or no? All of these are polar protic solvent. So by this way we can explain how SN1 reaction depends on the solvent. Okay, next we come to the number 6, that is catalysis. Okay, number 6 is catalysis. Of course, of SN1 reaction, why the catalysis is necessary, and which one act as the catalyst will be discussed. So take an example of this one. So if we take an example of this one, that is CH3, 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 and the OH. Okay, and the OH. All of we know that it's a very bad living group. OH minus is a strong base. That's why its energy will be very much higher. So OH minus is a bad living group. OH minus is bad living group. Okay, but its neutral species, that is OH2 or water H2O, is very good, very good, because water is a very stable molecule. Everywhere is water. So first of all, if we convert this presence of H plus, concentrated H2, this very small amount of concentrated H2, 3 to 4 drops is sufficient. Then it will go to here, that is CH3 whole 3 COH2 plus. Understand? Now it can now leaves very easily, that is CH3 whole 3 C plus water. It's a very good living group. So to make the OH is a good living group, this one act as the catalyst here. Yes or no? This one act as the catalyst. That's why the dehydration of ethanol to the ethylene carried out in presence of concentrated H2O at temperature 170 to 180 degrees centigrade. So all the elimination, all the substitution or elimination reaction of alcohol is carried out by in presence of acid because it can catalyze this reaction. So we got the CH3 and in this will be the final product here. Okay, substitution product. It can give the elimination products also. This will SN1, it will be discussed later in this case. So the anionic and this one is corresponding neutral species. So all of this one, that is the RO minus is bad leaving group than the ROH. This one is a good leaving group because this one is more stable than this one. This is very strong base. This one is also very strong base. So the neutral species act as the good leaving group. So this one is the first catalytic technique, or you may convert this into the OTS. Yes or no? The OH is present here. If you reaction this with tosyl chloride, this is not necessary here. Tosyl chloride in presence of pyridine, then look at this group will be converted to the OTS. OTS. All of you know that this one is a very good leaving group. Okay, TS OH. This is actually not the catalyst. This is the technique how this bad leaving group can be converted to the good leaving group. Similarly, Ag plus or Ag2 plus, which can bind with the halide very easily, they can also act as the catalysis in the SN1 reaction. So such kind of catalysis is actually called acid catalysis because these are also acting with Lewis acid. So this one is this part, and the last part of the SN1 reaction is the problem of SN1 reaction. Problems the SN1 reaction. That is the rearrangement. Okay, rearrangement may have a problem. So take an example first. There is two examples. One is the alkyl shift and another one is the hydride shift. So now if you take this as an example, that is CH3, and this one is CH3 and hydrogen, and this one is Br. So first of all, it gives this one. In the SN1 condition, it will give this, that is CH3, and this one will be CH3 plus. Look at this. This is clearly 2 degree carbocation. Now, if this methyl minus with its electron pair shifted to here, so that means this one is CH3 minus shift. Then what should happen here? It goes to the CH3, and this moves from with its electron pair. So plus will be goes to here, and CH, and these two CH3 will be present here. And clearly this one is the 3 degree. So look at this substrate gives the 2 degree carbocation. But as this one is more stable, so that is the driving force for this stable. This is the driving force for this methyl minus shift. Methyl minus will shift it to this and gives this corresponding 3 degree carbocation. And we got the N-nucleophile minus and product. So major product will be appears from this as it is more stable carbohydrate. So this is the called the alkyl shift, and we have got the corresponding product from here. So another rearrangement may be possible. That one is called the hydride shift. So after hydride shift, if the system is intermediate will be more stable, then this will be more favorable. So now if we consider this, Br is here. So now it gives the corresponding carbocation is this one, that is the benzene ring, then goes to the plus charge here. One of the hydrogen is present there, it is 2 degree carbocation. Yes or no? It is 2 degree carbocation. Now, if that hydride will shift to this, okay, that is H minus shift with its electron pair, as it is positive charge, so electronically deficient, but electronically rich. H minus will be rearranged to here, and we got this product. Yes or no? Clearly, this one is now stabilized by the benzene ring. This one is called the benzylic carbocation. Benzylic carbocation. Yes or no? This one is called the benzylic carbocation. It will be more stable. Yes or no? the resonance is possible here, more stable. So the product will be corresponding of this one. So these are the main problems for the SN1 reaction. Apart from this, there are too many examples or others also there, but these are the few characteristics and overall idea of the SN1 reaction. Okay, so this one is your first part of this, and the second part will be discussed about SN2. Okay, so today, bye.